this is about the layers of the atmosphere. The picture I have shown up here, you have the four different layers that we're going to be talking about: the troposphere, the stratosphere, the mesosphere, and the thermosphere. It goes from ground surface all the way up to the top of the atmosphere. And the atmosphere itself is pretty thin. If you were to imagine an apple, and that entire apple being the Earth, the skin of that apple would represent the atmosphere. So extremely important, obviously, for life, but overall, compared to the Earth, it's an extremely small portion of the entire Earth system. The lowest one closest to the ground is the troposphere. That's where we live. It's where the weather takes place, and the weather wants to stay in the troposphere as well. There's only a couple instances where it actually will move into the next layer, the stratosphere, and that's if there's an extremely strong thunderstorm, and a severe thunderstorm at that, and it's so strong the updraft will pop up into the next layer. And if you're at a distance, you can actually see that. It's called an overshooting top, and it's pretty impressive looking, and that tells you it's an extremely strong storm. But otherwise, it all wants to stay in the troposphere. Now, when you go up in the atmosphere, you know the temperatures generally drop unless something weird is taking place. You go up a mountain, you know it's going to be colder at the top of the mountain than at the bottom of the mountain. So the troposphere generally has decreasing temperatures. Once the temperatures start to become isothermal, where they stay the same for a short time, maybe even a long time, it just kind of depends on the layer, then that tells you there's a transition into the next layer. So that'll give you an idea that you're heading into a different layer, of that isothermal profile on a lapse rate, which is what this is called. The next layer up is the stratosphere. Once you're really getting into the stratosphere, the temperatures increase quite a bit, and that's because the ozone layer is present there. Ozone's job is to absorb ultraviolet radiation from the sun and protect the Earth from it. Obviously, it doesn't do a 100% job, and that's because of issues that have taken place over, many years from, humans having been the issue. So generally, it's supposed to filter out all of it. And actually, life could not have ever gotten started on Earth if it wasn't for the ozone, because ozone can be very damaging to plant life as well. So it's an extremely important part of the Earth system. As you go up into the next layer, the mesosphere, of course, there'll be a portion where you'll hit the stratopause, which means the temperatures become isothermal until you're switching into a different layer. In the mesosphere, the temperatures drop dramatically and very quickly. A recent discovery in the mesosphere has been polar mesospheric clouds, what they call noctilucent clouds, and they haven't really been observed back in the past, like back in the 1800s when they started doing some simple weather observations, but they've now been really discovered, and they're really faint. They're made of water or ice crystals, and because water vapor as you go up decreases quite a bit, by the time you get any water vapor up in that layer, it's extremely limited. So these things aren't really easy to see with the naked eye. They're relatively new being discovered, so they're trying to figure out exactly what the purpose is behind those, and usually don't see them until summer. And when you do see them in summer, they have to be illuminated by the sun barely, or detected in other ways that we have. And you usually find them at latitudes like 50 north and on up to like 70 degrees north or south. So we don't know a lot about it. I think it might be telling us that there's some kind of changes going on in the upper atmosphere, but other than that, there's a lot of discovery going on there. But anyways, other than that, that's nothing else goes on in that layer. The next one up, the thermosphere. And again, there's a mesopause in between. Temperatures will come isothermal, and you'll switch to the next one. Temperatures increase dramatically. The ionosphere is there with a lot of charged particles, and that's where the space shuttle comes in, and you always hear about, it's got to go through this really super hot area, and they have to have those special tiles on the space shuttle in order to get back into the atmosphere because of it, and that's at the thermosphere level. There's also, you would see the Aurora Borealis or the Aurora Australis, which is the southern lights, in this layer as well. So basically charged particles interacting with gases, and it puts off those really cool looking colors. And those charged particles come from the sun. So after that, you're going to the exosphere, which is you're entering into space, and it's not technically considered the atmosphere anymore. And the sun is a star, extremely important. Obviously, it gives us our light and our heat. Now the sun, there's a bunch of statistics up here. I would never quiz or expect you to know all these details of the sun, but just something you can look at. That the light traveling from the sun to the earth takes about 8 light minutes to get here. And its temperature, as it goes for most stars, it's pretty boring star. Think about it, we'll just call it a boring star as you compare it to others. It's not very hot, and it's not, it just doesn't really do anything that's like that spectacular compared to all the other stars out there, but obviously extremely important and like wonderful for us. And the Earth is in the right position to get enough of the radiation from it to be, well, perfect. So stars are made of mostly hydrogen, a little bit of helium, and then there's about 1% trace of other elements that are present. The sun itself produces all the radiation that it gets from it from within the core, which uses hydrogen fusion, which is a really efficient process. When it's created, of course, when it's created inside of the sun, by the time it makes it out to the surface and then, of course, away from the surface towards us, there's a huge loss in between. So that has a lot of implications, too, for the sun itself when we're looking at just how steady the sun actually is. The sun gets what they call sunspots, and that's because, well, it's so big that it rotates at a different rate from the equator versus at the polar regions. So it has this different rate. So what it ends up doing is it kind of tangles up the magnetic field within there, and for a lot more complicated reasons, it ends up creating an area that has zero magnetic field, and what we end up calling a sunspot. So it's this darkened area on the sun. They can be big and they can be small, and even when I say small, we're talking about lots of Earth-sized planets can fit inside of it, so they're all relatively huge when we look at them comparing. But on the sun, they can be tinier versus even larger. These sunspots were discovered by Galileo back in the 1600s when he did a lot of studying of the sun, which was an important thing because at the time they thought the sun was perfect and had no issues whatsoever, and he discovered, oh hey, look, there's spots on the sun. The sun does change, and that was a big deal back then, as they were a lot of church hold at that time, and it was extremely it was bad to say that the Earth the sun was different, because the sun was supposed to be absolutely perfect, and he discovered that it wasn't. Well, sunspots themselves, what they do is they block out the radiation behind it. So this little blackened spot, what they call the umbra and the penumbra, all that is blocking out radiation that should be coming out from the core of the sun out to the surface. Well, it's blocking it, and it can't get out. Well, it's created, it's in there, it's going to get out one way or the other. So what ends up happening is you'll find that around the edges of these sunspots, you'll have much more intense radiation coming out of it. So if you got more intense radiation being thrusted out, kind of like a wind tunnel effect, if you will, and you have a lot of these, you're going to send that like concentrated area out into space. And if that happens to be facing the Earth, so that portion of the sun that has all these sunspots are facing the Earth itself receives more radiation. If that happens over a longer period of time than normal, then you're going to get more radiation at the Earth's surface. On the flip side, if it gets quiet, there's what is called solar max and solar minimum, where there's a bunch of sunspots for roughly 11 years, and then there's very little sunspots for roughly 11 years, for this whole total cycle they call the sunspot cycle. And if you don't have any of these things on here, and nothing's being blocked, and the radiation is just coming out like it normally should, then everything is fine. And you could end up with times where the Earth isn't getting as much solar radiation, and it'll cool down. And that's happened several times in the past. There was one in the 1600s, kind of moderate minimum, where they didn't have very many sunspots, and the Earth cooled, and there was a mini ice age. So how much radiation you actually get from the sun is extremely important. It's what they call the solar constant. It's not really constant. It goes up and down. You get more radiation from the sun for a certain period of time, and then you get less, and it'll toggle back and forth. Let's see. So you get everything off the electromagnetic spectrum from the sun except for cosmic rays. Cosmic rays come from stars that have died. Obviously the sun hasn't died, so we don't have any of those. Our atmosphere protects us from everything up to visible light. Technically, we know that ultraviolet radiation does get to the surface. It's not supposed to, but it does. So it should protect us from ultraviolet radiation all the way up. It even protects us from cosmic rays. So it does an excellent job. The ones that are the longer wavelengths, which have less energy, like visible, infrared, all the way down to radio waves, those things can penetrate. So we get all that stuff from the sun. And let's see, another way to look at it is the longer the wavelength, the less energy involved, so the less dangerous, which is why radio waves and microwaves and the visible light that comes in isn't damaging to us. Whereas stuff that's smaller wavelengths, ultraviolet, causes skin cancer. We know X-rays, you can't have too many of those because those are obviously dangerous. And gamma rays and all those other types of radiation are extremely dangerous because they've got more energy in them, and they have more energy, more ability to destroy our cells in our body, which obviously is bad.